Hi everyone! The purpose of this next set of videos is to talk more about some of the content in Chapter 22, and we'll also talk about some important ideas that come out of Chapter 23. As you start to read Chapter 23, we're hoping that you'll notice there are a lot of ideas in there that are review from Chapters 21 and 22. So we hope that seeing more practice problems will help you. Reading about it again will help solidify some of the ideas. If you left our coverage of Chapter 22 and felt very confused, I want you to take a deep breath and know that you're not alone. We know that this content is challenging for a lot of our students, and that's why we've tried to put a lot more practice problems together for you here in this set of lecture videos. I hope by just going through lots more hypothesis tests that you'll really come to understand the terms and the ideas and know what all of this means. So we know there's a lot to keep straight, but again, we hope that practice is going to help. And if it's not helping, remember that we're here to support you, so please reach out and let us know if we can assist in any way. So before we get started, we kind of ended some of our Chapter 22 coverage by getting into this idea of two-tailed or two-sided hypothesis tests. And I found this interesting cartoon that I thought might be something nice to refer back to, especially if you get a little bit confused about why we would do a two-sided test, what that looks like. We'll go through some more practice problems in this set of slides. So if you left Chapter 22 feeling like you just don't understand why we're doing this and what it all means, hopefully it'll make a little bit more sense now. So let's begin with a practice problem, and hopefully this will be a review for everyone. This is a what do you think type problem. So a claim is made that 89% of college students plan to drive to their spring break destinations. So we're starting with a claim about a population parameter. You believe this percentage is too high. You survey a random sample of 80 college students and find that 75% of them plan to drive to their spring break destinations. Our alternative hypothesis would be what? So again, when we give you these kinds of problems, we generally will begin with the claim about a population parameter. So here that claim is that 89% of college students behave in a certain way. Now you take a sample, you don't believe this claim, so that's why you're conducting a hypothesis test to begin with. You then take a sample of a certain size, here that size is 80, and you find that your sample statistic is 75%. So 75% of your sample falls into this particular category. So hopefully you're automatically looking at the answer options and you're noticing that we give you information in the form of proportions. So remember, if you have a percentage, you can convert that to a proportion just by dividing it by 100. So our population proportion would be 89% divided by 100 would be 0.89. And our sample proportion, or p-hat, would be 75 divided by 100, or 0.75. So I'm hoping you're looking at these options and automatically excluding A and B. So why would A and B not be our answers? Well, remember that our hypotheses are always written with respect to our population parameters, not to the sample statistics. 0.75 is a sample statistic. Now we're left with C, D, and E. And we are told here that we believe the original claim is too high. We believe 89% is too high, which means we think something lower than 89%, something less than 89% is what's actually going on. So the best option here would be D. We have our symbol for our population parameter. We have the sign. In this case, it's the less than sign because we believe the initial claim is too high. And then we have that initial claimed value. We have that population parameter in our hypothesis. So again, it's going to be really important to recognize what your null will be, what your alternative will be. Remember that your hypotheses are always written with respect to population parameters. And again, we'll practice this a lot more. So if it's still not making sense, I hope by seeing many more examples, it'll really start to click. So here is something that I showed you in the last set of slides. So I'm not going to spend a whole lot of time here, but I just wanted to remind you that when you have a null hypothesis, you always have the equal sign. So the null is the claim about a population parameter. The alternative hypothesis can have one of three possible signs. And so it's going to be important to understand, should I have a greater than sign, should I have a less than sign, or should I have a not equal sign? So being able to recognize some cues from the problem to help you decide which sign you should have. That'll definitely be something you'll need to know. When we have what we call a one-sided or one-tailed hypothesis test, that means that we're testing or we feel the claimed value is going to be in a particular direction. So remember, we might have something like this. So the null, again, would have the equal sign. Here, mu equals 10. Maybe the claim is that students get an average of 10 on a particular type of test. Maybe you believe they get more than 10. Or maybe you believe they actually would get less than 10, and that's why you're conducting the hypothesis test. So notice in each case here, we're limiting our attention to one side or one tail of that sampling distribution. We think that the results will fall either greater than the actual claimed population value or less than that claimed population value or the claimed population parameter. Now, a two-sided test or a two-tailed test is where you begin the test by not believing that claimed value. You don't think that's right, but you're not really sure if the true value is greater than or less than that claim. You just think it's going to be something different. So you'd have a hypothesis or an alternative hypothesis that would have the not equal sign. So down here, notice that we're suddenly focusing on proportions. The null, again, always has the equal sign. The alternative would have one of these three signs. And one thing I'm hoping you're paying attention to is the fact that when you write a hypothesis, there are actually three important elements that you need to include in your hypothesis, whether it be a null hypothesis or an alternative hypothesis. We start with the symbol for the population parameter. We then have the actual claimed value of that population parameter. And in between those two things, we have a sign. The null would always have the equal sign. The alternative would have, again, one of these three signs. And this is just important because if we ask you to write a hypothesis, we're going to want to see those three parts. If you skip one of those parts or don't feel like you need to include it, then it won't be correct. So really pay attention to this and make sure that you include those three parts. Now, we talked in our Chapter 22 presentation about the fact that if you conduct a two-sided or two-tailed test, you get your p-value by doubling the one-sided or one-tailed p-value. And I know that's maybe a little confusing as to why we would do that, but I again wanted to just kind of walk through how you would do this, and hopefully it's going to start to make sense why this is the case. But this is what you always do whenever you're conducting a two-sided or two-tailed test, regardless of whether you're working with means or proportions. So it's the same. If the alternative is two-sided or two-tailed, you will always do this. So here I have just some steps that you'd want to think about in terms of determining your p-value. And I showed these in the last set of slides in the last lecture for Chapter 22, but I might have left out a little bit of the details, so I wanted to show this again. And again, the idea, if you're kind of trying to visualize this and think about what's going on, the idea is that we, right from the start, we're just not really sure in which direction our results will be. So remember, with the sampling distribution, it's centered at that claimed population parameter. So let's say this is a test about means. It would be centered where mu is. That's where the sampling distribution is centered. We're not really sure when we conduct a two-tailed test if our sample statistic's going to be up here someplace or is it going to be down here. So we think it's going to be something different, but we don't have enough information to say for sure it's going to be in one particular direction. So to cover ourselves, we want to look in both directions. Now, ultimately, our sample results will fall in just one tail. Maybe for instance, they'll fall over here. Like right here, maybe they'll fall. So they're falling in one tail, but again, we have to think back to what were originally predicting would happen. Originally, we weren't really sure where they would fall. We thought they could fall in either direction. So even though the sample results actually are only on one side or in one tail of the distribution, we need to double that. And by doubling that, we're going back to our original hypothesis, and we're just following through with looking in both tails. So doubling it is our way of looking in both tails. And I know that might not make perfect sense here, but hopefully it's starting to make some more sense. So we just have to carry things through. If we said originally we were going to look in both tails, we have to follow that through. And our way of following that through is by finding the one-tailed or one-sided p-value and just doubling that. So doubling it means taking into account the other tail as well. So remember, here are the different steps, and we'll work through these. We worked through them a little bit last time, but we compute our test statistic just as we normally would. So there's not a special formula here that you use if you're doing a two-sided or two-tailed test. We use the regular formula, we find our z. Then we have to think about whether z is negative or positive. So if it's negative, we would go to table B, we look up that z statistic, we find the percentile. If it's positive, we go to table B, we find a percentile. We have to subtract that percentile from 100 to take into account that our test statistic was positive, meaning it's up here, and we want to find this upper tail. So remember, table B always gives us the lower tail. Now what we do is we take whatever we get in step 2 and we multiply that by 2. So we're going to get a percentage in step 2. We just multiply it by 2. And then we divide whatever we get by 100 because we want to convert our results back to a probability. So remember, p-value, or a p-value is a probability. The p in p-value stands for probability. So we're trying to get you to always convert now what you're getting in table B, the percentile, to a probability and to express the results as a probability. We're then going to compare that probability we get in step 3 to whatever our original alpha level was. So if alpha was 0.05, we take our two-tailed or two-sided p-value and just compare it back to 0.05. So you don't have to do anything with alpha. You don't have to divide that by 2 or multiply that by 2. You keep alpha as it is. All you're doing here is taking the p-value and multiplying that by 2. Okay, so let's see this in practice. We'll go through some examples here. Let me see how we're doing on time. So I think what I'm going to do is I'm going to actually pause this video, and then we'll come back and we'll work through an example where we can kind of go through these steps. I'm hoping that something a little bit more concrete will help things start to make more sense. So hang in there with me. I know it's confusing, but I promise that we'll do lots to try to help you see the light, and we'll try to help you make a lot more sense of this.